All right, last piece. Good, good. This is fun. Fun. So this is ridiculous. This is work that started for me. Let's look at this. Work. I think it's under Contagion. Nope. Networks. You know, I put it under sociology, which is ridiculous. Sociology. Yeah, but the start of it is it's this thing. It's up-down thresholds, 2005. So the work for this was published in 2013. And there are various reasons for that, and I'll tell you why. I mean, part of it was a very interesting simulation, interesting results, but analytically it was difficult to get at. And so we got somewhere with it. It's very hard to solve the whole thing, as I'll show you. And this ends up being work between myself, Cameron Harris, who's an alum of Story Lab, and Chris Danforth. So, and in fact, Cameron made it into his master's thesis. So I'll show you some fun results. I'll show you some videos that he made, and we'll go through the setup. Some of you have definitely seen this. Okay, but I'll explain it in a sort of a different way, perhaps. So, yeah, the idealized hipster effect. Very idealized, right? So this is going to be inspired by, but not applicable to reality. So we have, and the idea is that people want to be cool, right? They want to be like each other a little bit. So being cool, you can't be just completely different. You have to belong to some group a little. So there's that. You start wearing clothes that the cool people wear. But then if everyone's wearing it, no good, right? So you have to turn it off. So people, before we had just this threshold story, so when enough people do something, you're like, sure, I'm a human, I'll be like you. But it never switches off, right? If everyone's doing it, you're like, this is even better. Okay, we want to add a very reasonable human behavior, which is not wanting to be exactly like everyone else. All right, let's use this. Okay, so these two papers are a pair. So physical review letters, very nice. You know, this is the venue if you want to publish in physics. It's the top journal. So a ridiculous thing. It's limited, imitation, contagion. So it's imitation but limited. So it's lick, and we get to say this: chaos, universality, and unpredictability. Yeah, really great title. And then this is the piece that they're sort of companion. They're a pair, which goes into some good analytic results. We had a fantastically long title for this, but it's just fantastic. Had every word we could think of, but there was a limit, unfortunately. So it got blanderized. Okay, so this idea. So what if these individual response functions that when we talked about contagion, this is a big deal. They're not monotonic. They actually drop off at some point, right? So you've got two thresholds now. You've got the threshold at which you decide that this is not good. Okay, so activation, deactivation. So this is a funny exploration that's possible. I'll show you how we get to it. But we want to look at deterministic and stochastic versions of essentially the same thing. Okay, so there'll be 4 different cases, right? So we'll have fixed networks or random wiring networks, right? So that's the structure part. And then we'll have kind of a stochastic response function, a probabilistic response function versus a deterministic one. So this is a deterministic one. You will always, whatever the fraction line's in here, you see a fraction of people around you doing something, you will always turn on, right? Probably 1 that you turn on, probably 0 that you turn off. Sorry, probably 1 you will turn off, right? Deterministic. Okay, so these are the 2 fundamental types we'll talk about, and I'll show how we can glue them together. They don't look like each other at all, but there's a nice connection we can make. This is it's the tent map. It's a beloved map in the dynamical systems in chaos. You know, for my masters, I spent a lot of time thinking about this guy before I went off to the fairy map, which is a cool map. F-A-R-E-Y, which is gives you intermittency, one of the 3 routes to chaos, right? So this one gives you, it's in the bifurcation type story. Okay. All right, so we know how this thing behaves. But we're not, it's going to be a bit different. I'll show you what the standard version of the tent map is, how that works. But we're going to talk about this as being an individual response for everyone. So, and then this kind of thing, right? So now we have a nice clean story. This is a probability that you turn on and off, right? This is probabilities that an individual turns on and off. So it's between 0 and 1. You will absolutely be on if exactly half of your friends are on. You'll absolutely be off if all of your friends or none of your friends are on. But other than that, it's probabilistic. And this is completely deterministic. Okay, so the tent map, superhero, fun thing to vote. So it's piecewise. That makes it a little tricky. You know, it's got a nasty little thing for differentiability issues right here. But that's cool. That's all right. So the usual thing that we would do with this is we're not worried about networks, right? We're just thinking about a system. We just have one quantity that gets updated by being pushed through this tent map sausage factory, right? So typical, here's a little guy, starts here, right? Here's our initial condition, and we use our little cobweb thing, which you guys just did for, yeah. And this one, there's a fixed point sitting right there, so that's good. So this is a tent map where, as I was showing you, there's R is this overall parameter for the tent map. We'll move away from that in a funny way, but this is just simply a parameter that gives you the slope and consequently the height of this point. Right? So you can dial that thing up and down, you get different behaviors. When R in this case, I guess it's not written down, R is, you know, what is it? This is Rx. So this is a little bit greater than 1. We've got a nice fixed point there. Right? That's still true when we increase R, right? So it's departing from 1, it's increasing. And then it starts to go bananas here. Yeah. What's that? This one? Is it a period 4? Yeah, so that's R equals 2 actually. But from this definition, sometimes there's a half in there. It was just this. So it's got a slope of 2. So it gets to 1 after half of a, yeah, right? And the opposite guy's coming here. So starting at the same point, it's all over the place. Now, that's the limit which we tend to go to, right? We start at R equals 1 and then we dial it up to 2. So we have this range. And from R equals 1 to 2, you can plot the fixed points. And you can plot, in fact, not just the fixed points, but the time they tend to spend at points, right? So if it's periodic, you'll plot a density map, which it's probability density. It's the long-term probability of where your iterate will be, or an invariant map. Invariant density is another way to think about it. So you turn a dynamical thing into a geometric picture, right? It's just sort of a long-term. So for our R equals 2, this is actually a uniform distribution here. So if you pulled this out and turned it around and looked at it, it would be a uniform distribution. So you let this thing run for a bazillion time steps and then sample where it is. The probability that it will be anywhere is 1. It's uniform, right? So it wanders all over the place in a nice equitable fashion, right? It doesn't have any kind of funny. Whereas, so back here, this is the fixed point, right? So it's here. It branches, starts to have 2 little fixed points. And then quickly you get into something where you don't just have a simple periodic structure, right? It's actually filling this up densely, which is different to the classic logistic map, which we'll talk about. So it's filling this up densely, but it has different density, right? So it doesn't spend as much time in here as it does here.
How is it different from the logistic map? I thought that the tent map
Is in the same box.
Yeah, I thought it was like I thought we used it to describe them.
You can connect them, yes, but they have a, I'm going to say they have a quantitatively different kind of class of, orbit diagrams, right? Because it's filling space here. So this is what the tent map looks like. So if we've got the tent map sitting in the system, and we're going to put it in the system in a funny way, right? There's no network story here. This is just one thing being iterated. We're going to somehow put it in the system. You have to think what we're doing, right? Then yeah, we might see this somehow, appearing, right? That's what you might expect. You might expect this appearing in some way. What we're going to do is stick with this one, the r equals 2 case. We won't actually vary the slope. We're just going to have the r equals 2 case, so that should give us this bit here. All right, r equals 2 case. So what happens if we now have nodes and they have limited information? So they're going to make their decision, it's a tent map, they're going to make their decision. This is also deterministic, right? So you map to a particular point. Now we're going to turn it into a probability. We're going to say, okay, you see a fifth of your friends are on, and you're going to, with probability, whatever it is, I guess 0.4, are going to, right? That's the probability you'll be on the next time step. So we're going to put on a sparse, we'll just put on a pure random network, these things that don't exist. We're going to start with them. We always start with them. So just a good old Poisson degree distribution. And our usual thing will vary this average degree business, right? Great. Okay, so here's the way we connect the deterministic response function here to the tent map. And here's another kind of thing here, right? So there's 2 pieces. So what we're going to say is, in this case, for this case over here, let's randomly choose the up threshold between 0.5 and randomly choose the down threshold between 0.5 and 1. So that equates to randomly choosing a point in this little square, right? So the up threshold is between 0.5, down threshold is between 0 and 1. So if you do that and you average over all of these guys that you're getting out, these little deterministic response functions, so now you have a bazillion nodes, they all have a fixed response function. It's deterministic. They're purely predictable. They don't have any randomness in them. But you average over all their response functions, then you get the tent map for r equals 2. So, sort of as viewed from as a whole, if you average all, you sort of threw them all in a big soup, on average, that's how they're behaving. Right? So if you polled them all together, they'd on average do this. This is one where we say, we'll put it in this triangle. The up and down thresholds are in this triangle. So the down threshold is always greater than the up threshold. This is just a simple thing to do. It's uniform in here. And that gives you a little parabolic guy, which is not bad. That's enticing because we could get to the logistic equation. But we love this guy. That's pretty well understood, so we might as well start with it. But in general, you could imagine these two are uniform distributions. You could have weighted distributions. You could make some combination of these things behave as any overall average response function. Average out to some overall response function. All right, so we're going to look at the temp map. And so here are a couple of things. So this is an average, so there's a random network, say 10,000 nodes, I think. Average degree of 5, so not, but connected enough, right, what's the critical average degree for pure random networks to have a giant component? Yeah. 1, yeah. 1, so, which is kind of weird, but it is 1, right? Yeah, so, well, there's an aside there, but I'll tell you later. So, it's 1, and so this is nice. This is a giant component here, right? For sure, it's 5. We know that, in fact, you get a hairball at 4, right? So, all right. So what's happening now is everyone has on average 5 friends. They look at their 5, 6, 7, 3 friends. They look at their states, and they fit it into the little tent map response that they have. 2 out of 3 are on. They go, okay, 2/3 is here. That's like this bit, and then they flip a bias coin. More chocolate? Okay. That's all right. You should, okay, fetch and eat. Yeah. Okay, so this is what happens in this case. You're running along in time. This is the average fraction. I'll have lots of different things here. These are ancient. The fraction that are on, right? So the overall fraction are on. This is not going to show you who's on, who specifically is on. It's just the overall fraction is on. So it's stable if you look at the overall fraction. Some are switching on and off, though, and we'll get to that. Right, so it's pretty stable. So it's just below 0.6. And if you average this over some time, you throw away the initial ones, then you get this invariant density, right? That's something we want to get to. What does this system look like on average? So you have to throw away any transient behavior, some initial stuff, settles down. Like, okay, good. So this is kind of what this whole thing looks like. Right, that's one. So this is varying, it's hard to read, but this is average degree 5, 10, 18, 22, 24, and 30. And they're just sort of chosen. I mean, there was a bigger list, but they were chosen in this way. So you see a funny thing start to emerge. You're connecting them more. Everyone has a temp map with r equals 2, which we know by itself is fully chaotic, fully mixing, right? If it was just done by itself. You think about the limit of average degree going to infinity, everyone's connected to everyone else. So everyone knows what the average score is. So it should behave like the temp map in that limit. That's an important point. It should behave like the temp map in that limit. Okay, so get to 10. Suddenly we have a bimodal thing. They're switching on and off, but there's a big 2-cycle kind of thing. And so this is what you see on average after some time. If you go up to 18, it bifurcates, and you get this kind of picture. So it's actually switching around these 4 things. This is 22, and you start to see it kind of smoothing out, and this one's smoothing out. You might say there are kind of 3 things in here, maybe. But so this is a bit strange. This is upsetting, I think, initially, or just it's both upsetting but fascinating, right? So this is one network. This is one network. So you make the network, it's fixed, right? And everyone has and you also give everyone their little deterministic response function. You draw them out of a hat, but you hand this one to, Elspeth, and you say, okay, this is your response function, you keep it, okay? Augustine gets one as well. Courtney, yeah. Okay, so the ABCs are usually not very good, right? So we need better ones. Brian, that's for Brian Lara. Okay, so really weird thing. You get that same kind of behavior. So what's weird about this is one network. Everyone has their own response function. All we're doing is we're starting at different points. We're just going to switch on one and let it run. It's completely deterministic. There's no probability in here anymore, right? Yeah.
Each of these are the same network. You just started with different points.
All you do is start at a different point. You should think that, well, it might matter. I mean, you've got someone who's right on the edge and their friend has tons of friends and it just dies straight away, right? So you could think that. Or, so you might think there's a lot of things that don't take off, but if it does, it should kind of settle down into some pretty big pattern. So initial conditions shouldn't matter too much. You can imagine it's a network, so yes, it could be that it fails straight away and the whole thing goes away. But if it takes off, it should start to kind of, we've got a random network. It is deterministic, but you might expect it to kind of find a thing. And it has to find it's deterministic and it's a finite size, so it has to find a cycle eventually. It can't explore an infinite thing. Yeah, so what happens actually is it's behaving kind of like we saw in that previous picture. It's exploring some different states, and then it goes, but it settles in different ways, right? So this one has 2. This is bimodal, depending only on the initial node. So you're getting that pattern. There's this one. So this one didn't break.
Do you think that would settle?
So we'll get to that. It was a very good question. We'll get to that. This one, these are 2,000 time steps. Each time step, everyone gets a chance to update. This one is a pretty wide one. What we'll see is, in fact, it looks like period 2, but there are tiny little periods in there as well. This is unreal, this thing. Again, nothing to do with reality anymore. What's that? Yeah, so Cam did his master's on this. We're 2 papers, yeah. I think you, but we said, this is a little thing I cooked up in 2005 and then just sat on for a long time because it was insane. But turns out to be lots of fun. All right, so let's try higher values of average degree. This is average degree of 100. And you think maybe that might help, right? Okay, not bad, but it's really starting to spread out. So it's every node is polling a lot more. They're becoming more like each other. Okay. So it doesn't quite, that jump, is that right? Yeah, kind of awkward. Actually, look at this though. So that was 2,000 time steps, 2,000 time steps, similar thing here. 10,000 time steps, it actually collapsed. So this is Eric, your question. It collapsed.
Yeah, that was that other.
We made it to, this is a very dense thing. There's 100, on average 100 edges. I mean, so they're all 100, a degree of 100. So they're all, polling each other very well. But it collapses again. This time after 4,000 iterations. So you don't expect this, right? This is doing a great job. It's going all over the place. The average number of infections is wandering, and then it's just stable. Okay, so here's an overall picture of what's happening. This is our tent map. This is just for the tent map by itself. This is the classic logistic map, again, just by itself for a particular height of the logistic map. It's a classic bifurcation story. Oh, right, sorry, the height is the dial here, and the height is the dial here, right? So that's just simple system things. The dial now is the average degree. Different thing. So it's the average degree, and all the temp maps here correspond to this temp map. So you see this kind of behavior, it's a ghosting of this thing. You can see you'd have to stretch and move things around, but it's in this universality class. So we can kind of explain why that is, right? So it's to do with, whenever you have a map of the interval that has a quadratic maximum, so the logistic map is the paradigmatic example, but just as long as you have a quadratic maximum, then you get, and some other things, then you get, you're in this class. You get this classic bifurcation story. So you might think it sort of might end up looking like this. Even though we're doing a very different thing, we're tuning the average degree. So connectedness is driving this route to chaos. All right, so let's look at some other things. One other thing you could do is, we'll have some pieces here. This is an old picture. Cam has a much more highly refined one that shows us some structure here, but this is asynchronous. Everyone was updating at the same time. So a simple thing to introduce is alpha, probability alpha that you update. So when alpha is very small, there's some fraction alpha, of course, that updates every time step, but the chance that someone right next to you does is 0, so it becomes effectively asynchronous. And so this is just weird. It's a different kind of bifurcation diagram. So this is something where we're driving the synchronicity, right? So as we tune from down here, very infrequent, it's one at a time, basically. Here, everyone's updating at the same time. So we go through a different kind of bifurcation in terms of the infection level. Okay, so this is actually what it looks like in this refined version. That's an old one. You can see it's much more detailed and highly resolved. And in fact, there is this ridiculous line here, which it actually occupies. The system actually occupies. All right, fine. So, okay, so I've got a few videos, courtesy of the Camster. So this is how the bifurcation diagram is going to change as we increase average degree. So average degree is growing, and this is the one you just saw. This is a function of the updating rate. So eventually it should get to that funny dense one that splits. But it looks all the way up until it does. It looks very much like the logistic map. So I'm going to show we've got two of these, and then others of actually little small networks with you can see who's turning on and off. Cool. I think it's going to go to 100. It's just a really, really weird system. All right, so there's that one. So now we're going to increase we're going to start with a right. This is the synchronicity parameter. So again, this is average degree. So the more and more synchronous the system becomes, the more it turns into a logistic map. We'll get to 1. We'll get close to 1. Groovy. Start to squish in. And it's pretty, this is a fair way. 30, I mean, it's sort of a funny transition. 30 is that's really connected, super connected. This is 10 here. Oh, they're huge, yeah. I mean, they feel really big, right? Again, this one is where you have a giant component. Implies, yes. Implies a new field. Okay, so this is average degree 6. Everyone's updating at the same time. And so here's the little plot of how many are active as a function of t. And so this is something you couldn't see from the initial pictures, but it's going to stabilize. So in terms of how many are infected, it's pretty good. But you can see there's this pulsing, right? At any given time step, from time step to time step, it's switching. So this overall signal says, nothing's, right? It's pretty constant, but the details are changing a lot. So that's going to be, so there's 1,000 nodes. This is some fraction that's not shown here. This is the largest group that is actually changing. Okay? Super groovy. Just really groovy. That's my little... Okay, I think we got the plan on that one. So we'll go up to a higher, okay, this is average degree 11. So much goodness. Look at that. Look at what he's done. I mean, this is just wrong, but that's pretty good HD, 1440. Oh, that's good. So this is one where you end up with actually 2 states, which you can see it on and off like a tree. Yeah, that's on fire or full of fireflies. Right. So this might be period. So there's a dominant period 2, but it could be period 4. This is messy. It's small. It's 1,000 nodes. It's not enough. But this could be something it's only average degree 11. So I think with more nodes, it should be actually period 2. So in this case, again, everyone has a tent map response function. So we'll get to the one where they have a fixed response function. Okay, so we see what's going on there. So on, off, yep. So which we saw in the previous one, but it actually balanced itself out to give you what looked like a period 1 thing. So there's the micro periods. There's a period, what I'll call the micro periods, the periods of the individual nodes. And you've got a whole distribution of those. And then there's the macro period. What's the whole system's average behavior look like? Only crazy people would try to play with that. So shared stochastic map, okay, yep. And now it's pretty dense. It's taking off, and this should kind of go all over the place. Yeah, average degree 30. This is getting well out into the bifurcation diagram. So it's becoming pretty unpredictable, right? It's a little, see that's interesting. That happens. There's a few in a row that were very similar. And we had that on some plots before. There are some periods of stasis, and then it explodes again. And eventually it actually collapses. But there are these little periods where it looks like the overall average is settled right down. So good. This one? I don't know what he used actually, yeah. FF, MPEG, or whatever it is. There's some good. You want the command line action? I don't know, actually. I need to ask him. Yeah. I know this other thing that I'll try and show you. Let me just break out for that one too, because that's kind of nuts. Let's let this one finish. So there's this guy. So this is okay. I should have showed you this before. This is ridiculous. This is the whole bifurcation diagram put together. So now we have. It's obviously hard to see, but there's and I can't quite tell you offhand which one is which, but there's alpha, the synchronicity probabilistic update thing, and then average degree on the other side. So if you take any slice, you're getting something that looks like this bifurcation diagram. So let's look at it from this end. There you go. It's nice. And then around here, it's just total insanity. So it's a it's a double bifurcation thing. It's ridiculous. It's ridiculous. So I wish I could zoom in on this. I should get Cam to record a flyby thing. Yeah. This thing is just coping, I have to say. It could blow up pretty badly. Yeah, I don't know about this thing. Paraview, so it's pretty cool. So yeah. It's truly nuts. So I think we can. Yeah, so there's all this good stuff, right? Slices and yeah. Okay. So let's not do that because I think I might hurt something. So, I mean, a crazy model, right? So there's this one. So this is going to be. So now they have fixed deterministic response functions. They're not temp maps anymore. They're fixed response functions such that they average the temp map. This is average degree 17, which is an interesting value. That's roughly where we had the one with all those different outcomes, which was just disturbing. I mean, really weird, right? Just you start it, everything is the same, except you start the contagion here, or here, or here, or here, and you get a fundamentally different working outcome. So we will exhaustively, for one example, we will exhaustively find all the possible outcomes, which is great, right? Because you can say, okay, I've got 10,000 nodes. I'm just going to start each one, let it run. When it settles down into a periodic orbit, find the macro period, find the periods of all of the nodes, bin them in a histogram, and then do it for every initial node. And then you'll get the whole story, right? For one particular guy. Okay, so how did that one end up? That was yeah, so this is one that splits, right? Yeah. Yeah, so there's this is like it has this little, it tightens up and you think, well, you know, it's going to be a single kind of thing, but then it pops out from there. So weird. Okay. So much higher average degree. They're deterministic. Now for the stochastic case, it would stay, right? It would sweep around and explore this whole space, looking like a nice bifurcation diagram thing. So it's happy. All these things are kind of popping on and off. They've got different periods. If you look at them, so this one's staying on, and then it went beep, beep. And now it's staying on or off, whatever it is. They have odd, right? They're not simple periodic behavior. And then this one is going to run out and might not. And then that happens. It toasted itself. That's really weird, right? Okay, this one is. Okay. It's a graph. Well, I'll show you some more pictures at the end. But generally, we avoid pictures of networks at all, right? So, and these are just linked to from the paper. So, but it gives you an idea of the hairiness of the thing. This one's clearly pulsing. It's going to Why are there two? Active fraction.
Oh, is it split up because they're so close together in the bottom?
Oh, that's what it is. You're quite right. I'm sorry. So this is actually period 4 behavior. It looks like this, and it's period 4. I mean, from a big point of view, it looks like this. So it's actually kind of balancing itself out, but there is a period 4 in there. Thank you. Yeah. Good. Good. Okay, so here are the last two things. These are the summaries. Let's see if we see what you think of this. All right, so temp map and logistic map, the classic things. We've got a nice little dashed line here to show you that this is what we get just from iterates of the maps of the interval. This has nothing to do with networks. These are just the universality classes. So here are 4 things from simulation, 4 results from fairly extensive simulation. So this is average degree 60. This is a case where it's a randomly rewiring network. So a node will have a degree 10, which means it gets to sample 10 others, but it's random. So we loosen the network up. And it has everyone has a temp map. So it's probabilistic in both, right? Lots of randomness, lots of mixing. That's good. Okay, so that produces this nice looking thing. It's from simulation, so it's, there's a limit to what we can do, but you can see that period 3 popping up here. This is, there's some striations in there, which I don't know what the deal is, but theoretically these should be very similar. It should be the same. This is the case where you do have deterministic response functions, but you're randomly rewiring. So that should smooth out the fact that you've got deterministic functions. I mean, the fact that deterministic stuff just starts to introduce some bumps is fine. But these theoretically are the same, and they look pretty similar. This one is slightly different. Now you have temp map response functions again, but the network is fixed. So your 3 neighbors are your 3 neighbors for life. Everyone has a temp map response function. And it still gives you the logistic map, but things have moved a little bit, right? So the first bifurcation point is moved. These guys have moved a little, not much, and there are again these striations. But theoretically, we haven't made much headway with that one. We can understand these quite well, which is a core piece of what Cam did. And this is very odd. This is very strange, but this is really, really what happens if you really run these things for long enough. So it's deterministic responses. Everyone has a response function that they're handed at the start of time and they keep. Right? So they're going to keep it, and we're going to, and the network is fixed. We just start at different points. So we make new simulations. Okay. All right. So so it looks good. This sort of matches up. We get bifurcations, and we get to 1 bifurcation, 2. So we're into period 4. Just get to period 8, and then there's a true collapse. Now, these end states depend on the network you've realized. They depend on the initial condition. As we saw, it matters even just for a fixed network. This is what I'm going to show you on the next slide. It's going to be this guy. So average degree 30. We'll look at one network, and choose different initial conditions. The next slide is all about one fixed network. This is to show you that as you increase log n, so this was for 10,000, if you go up even, so this is 3,000, 10,000, 30,000 to 100,000, right? This is the position of, as we could estimate, of this guy. So it's growing very slowly. This is log scale here. This is just a real scale. It is moving out a little bit, but this seems to be really, this is not an artifact of the size of the network. It's not going to make it, right? If we get to 1 million, 10 million, 100 million, we can't do that. But if we did, this is not going to just move out to the limit. This isn't some weird, as far as we could gather. Okay. All right. So now we're going to look at one network, average degree 30, deterministic response functions such that they sum up to, well, they average to give you the temp map. And everything about that guy is kind of here. So here's a summary. Right, 3 examples. They are sort of extreme cases. But this is time right number of iterations, so up to 10 to the 5. So this is 25,000, 28,000 iterations, which is that's a lot of iterations. If you're watching this thing going along, you're like, okay, that's a period 3 kind of thing. You can see it has these little, what am I using? Oh my God, spoon. It has these, you have to help me with this. They have these little bits where it gets a little uncertain, kind of goes all over the place, and then closes in, but then it's back, okay, I'm period 3. Whoop, 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 whoop. And out here, when it's collapsed, it is truly period 4, and there's 2 cycles of it. It's absolutely period 4. It's done, it's reached a thing that it cannot, because it's deterministic, it has to do this, it has to repeat at some point. But it doesn't repeat any of this stuff, it goes boop, and it's stuck on a period 4 thing. This is the narrowest collapse in terms of the overall width of the final state for the macro state. The widest one looks like this. And see this, this is ridiculous, you can't see it very well. There's a little line in here, which is what that box is. That's actually a little rectangle, which is what that box is. So we took that little rectangle, expanded it out, and these are time steps. So this one is actually period 4. It doesn't look like it, but there are tiny variations. You know, it could be just one node that's out of sync with everyone else.
Where it settles down on the left, that's what that box is.
This box?
That box.
That box is just 2 cycles taken. There's a gray line there you might not be able to see.
But
But
still period 4, even though it looks like it's
yeah, that's right. Right. So that's a bit of a thing to try and figure out, right? It really does look like period 1, but it has tiny little variation on top. So if you did a Fourier spectrum, if you did a Fourier analysis, you'd see, period 1 would really dominate, and there'd be this little on top. That's the same with this. This really looks like period 2. It's hugely period 2. But these things are, when it goes from here to here to here, that's not exactly, those points are not the same. They're a bit off. Okay, and then this is the longest collapse time. This one took close to over 160,000 iterations before it collapsed, which is just so strange. I mean, so when I first looked at, like I said, 2005, I ran like things that had words like Pentium written on them, and they ran for 3 weeks, and I just forgot about them, and they popped out these things. And I'm like, oh my God, this is so strange. So this is sort of the end result where it's exhaustively looked at. You can see, look, it went mad there for a while, and like, it's changed, but then it pops back out, and it feels like it's back in the same space. This is actually period 12, hard to see. It's dominantly period 2, but it actually has little, so it's the 6th one of these will look like will be the same as the first one. Okay, so this is so that's just 3 initial conditions, and they were emblematic in that one of them gave the smallest variation at the end, the other one gave the largest, and the third one gave the longest time to collapse. So they're interesting. This is the time to collapse. This is the distribution for, right, we're going to start with 10 to the 1,000, all these 10,000 points. This is it's an exponential, right? It's a cumulative thing, complementary cumulative. There's log here, so it's just an exponential. It has, this is the one that's over here, this guy. It's right there. It's just off by itself. There's a lot of, this looks good, you feel like something's okay, and then there's a bunch that take a long time. There's this one takes a long time, and then this one's just something else. Okay, this is, for contrast, this is one other network that's realized with exactly the same parameters. It's degree 30, same set of deterministic response functions. Again, they average, but it's a different thing. And that's its distribution of finish times. It's just different. It's exponential generally, but it's just a different thing. That's horrific. So this isn't even universal, even though there's so much, you have 10,000 things, you're sampling a lot, you're connecting them, there's a lot of randomness. But it's fixed. After you've done all this random stuff, you fix it, and that's enough to make it really different as you move from sample to sample. That's super strange. That's really strange. This is to show you, okay, what we're going to do is stack these end behaviors next to each other and order them by their variance. So this one is going to be here. This one is going to be right at this end. And then they're ordered by their variance. So you can see that all of them look kind of like order 2, period 2. And then they're actually colored according to their frequency that they end on these different values, right? So there's some different colorings in here. But basically, they all look like period 2, and they're sort of spreading. There's a nice array of those guys. This is a histogram for the micro period and one for the macro period. So so there are many. So these are over all initial conditions. So again, initial seeds. So you've got 10,000 initial seeds. You let every system run until it starts to repeat. And you go to every node and look at what it's doing. And so a lot of them are fixed, right? So this is the majority. This is log 10. The majority end up being fixed. Not majority, the modal one. I can't sum this in my head. There are a whole bunch that have period 2. There's one that has a period 132. It's crazy town. Some period 80 guys sitting in there. There's period 3 is unusual. You know, random networks, it's just unusual. You'd need some little triangle probably or something. 2 and 4, 6 and 8, those guys are there. So that must be period 10 in there, again, unusual. 24 sort of pops up, 48 kind of pops up, and 80 is not bad. Okay. And so this is the histogram for the macro period. So there are no macro periods that are fixed where there's really one. Yeah.
Why are odd number facts, even at the higher value, so unusual?
Why is what?
Odd number facts.
So I feel like this one, you know, again, you could find out by actually opening the box, but this, you'd have to get the ones that did this and then pull them out. Yeah. The vac got hurt for this. This, I think you need a triangle. So that's a problem there. And then going up, yeah, so there are no period 5 or period. So you just. It really hurts. Really does hurt. I mean, it's possible I understood that at some point. I mean, a little cycle of 5 is a weird thing to have.
Is there some special property of like even numbers just having to come together?
Yeah, it can't, so it has to be that, you know, there's a lot of switching going on. So powers of 2 are going to do pretty well. But that's not everything, right? I mean, there's 24. It's very painful. All right, that's a good thing to think about because it hurts. Let's look at the macro period. So this is all of these are hard things to compare. I mean, there's some subset of these go to each one of these. So there are no systems that settle down to just it never gets static, right? Never finishes statically. There are by this structure, is one of them ended up at period 2, exactly period 2. Which can't even be the one that's the thinnest. So there's one that ended up at period 2, that's log, yeah. And then a whole bunch of period 4, again, that's a 6, that's no good. That has to be 6, right? It's super weird. And these even ones, and there's one system that ended up at 240. And there are actually a good bunch at 120. 48, 24 stuck up as well. But, yeah. Trying to think how that one connects into that one. See, that's the thing. The micro period, there could be a period 132, but if everything else is balancing it out, this could be part of a period 2 or period 4. I mean, it just could be part of right, if everything else is in sync with it, wiping out its contribution. It's not obvious when you look at one. But sort of now, you know, this one, a lot of things are static, but the overall picture you've got some more stuff in here with period 12s and 24s and like this sort of silliness. It's going to be period 240, but it's going to look like, this sort of thing. So, I mean, it's just nuts. We've moved away a little bit in one direction that was sort of a fun thing to go in. And it's just surprisingly, spectacularly complex, which is good. I mean, I don't know where this goes from here, but it's, to solve this, to actually get into this analytically, that would be pretty impressive. To see what this is really adjacent to, because it is disturbing, right? It is disturbing. There's a lot of, I mean, maybe disturbing to you in a different way, but it's disturbing because you have all this deterministic behavior, and you would think, allied with that random initial stuff, the way it's built, that things should smooth out, but you actually get really big differences in the long-term behavior. Very, yeah. All right, so that's good. We're there. I have, a simple coda, which is just to say, do science. I usually say something like this, right? I've tried to explain this to myself over time. So modern science, this is the difficult part, find meaningful things, which maybe the example I just showed you is not a good one. That's why it took so long to publish. But it might be interesting mathematically, you see. So it's super fun too. You can't count that out. So find things that matter, describe it, and explain it. So that's surprising, really understanding that in a clear way, that this is what you're doing now, you're describing, now you're explaining. This thing can't be explained, but it can be described, And if you're a philosopher, you can explain it, but not describe it, so that's okay. String theory, similar story. And if you get through 1 to 3, you can create things and share. And that's really the sort of DECS, maybe with an F at the start. But that's the sort of the 4 big things. There's a little hedge at the start, which is make sure you're working on something that matters. That depends on other humans as well. That's tricky, yeah. Well, we're good at finding things that are fun to work on, but are absolutely unimportant. Yeah. So, but this unlocks, right? This is the whole engineering side of things, and design, and all sorts of good stuff over here. This is about truth. This is a little more about beauty. No beauty here. It's just truth. This is where beauty goes in. I think that's fair. So thank you very much, and you get to run away and come back.